Alright, so this is week 11, problem 11.17. Commercial refrigerator with 134A as a working fluid is used to keep a space at minus 30 degrees Celsius, rejecting its waste heat to cooling water that enters the condenser at 18 Celsius at a rate of 0.25 kilograms per second and leaves at 26 Celsius. The refrigerant enters the condenser at 1.2 megapascals and 65 Celsius and leaves at 42 Celsius. The inlet state of compressor is 60 kilopascals and minus 34 Celsius. And the compressor is estimated to gain net heat of 450 from the surroundings. So we are to show the cycle on the TS diagram and determine the quality of refrigerant at the evaporator inlet, the refrigeration load, the coefficient of performance of the refrigerator, and the theoretical maximum refrigeration load for the same power inputs to the compressor. Okay, so we can actually start by talking about this last one here, because we learned that for any machine, for any system that we can possibly create, we're going to be limited by our T source and T sink, right? Talked about that in the past, right? So we're going to have T, and then whatever we have in the middle here can be refrigerator, heat pump, whatever that is. We're going to be limited, whether we're going to work like that or work like that, doesn't matter. We're limited by those values, right? So in this case here, we can go ahead and do at least the beginning of the maximum coefficient of performance that we can have. We know that's going to be limited by the T source over our T sink minus 1. Okay, so before we do anything else, we can calculate what's the maximum coefficient of performance that this system could have. And notice that this has nothing to do with this guy here in the middle, right? It's only related with these two extremes here, which is our sink and our source. In our case, the source that's it's able to get heat out of the system is this 18 Celsius, right? That's the water that's entering the system and being able to carry away this energy, right? So that's the one that's acting as our sink, and then as our source, I should say. And the one that's the other extreme on this problem is our space, right? We want to keep it minus 30. So we'll be able to keep this guy minus 30 with a water that can come in at 18. Those are the two limits that we have within this problem. So whatever this guy in the middle right here does has to work within the boundaries of the minus 30 and the 18 Celsius. So in our case here, the coefficient of performance, the maximum I should say, will be 1 minus all in Kelvin, so 273 plus 18 divided by 273 minus 30 plus 1, minus 1. And all this subtraction, division minus 1, right? So the coefficient of performance, the maximum one we can have in our system, regardless of how good or how bad our refrigerator is 5.0625. Okay, and this is dimensionless, obviously. Okay, so that's the maximum we can possibly have. Okay, so let's start solving the problem now. Let's have a look at what we have and what's being asked. Okay, so let's look at what's going on. It's a little drawing of the system that we have at the moment. So let me zoom out a bit. Okay, so let's start. I'll probably do green. It's probably the easiest color. Let's start over here. Okay, so over here we have a high pressure, high temperature fluid. Okay, and to be able to remove some of this energy, some of this temperature, to be able to decrease the temperature, we're going to put this guy through a condenser. Now the condenser, like before, is not going to change the pressure of this guy. So this is isobaric process, right? But we have that water that's coming through this at 18, absorbing some of that energy and leaving 26, right? So we have energy leaving the fluid, the working fluid, and going to the water. Okay, so when we get to this other side here, we have a fluid that's at the same pressure but a smaller temperature. Then we're going to reach the expansion valve. And when we reach that, or throttle, also known as a throttle, and when we reach that guy, it's going to only allow a certain amount of steam from the R134 to go through, and that's going to mean that we're going to have a big pressure drop. So we have a big pressure drop here. Okay, and that pressure drop means that our temperature also drops, because we know that pressure is proportional to temperature, right? Ideal gas law. And so at the end here, when we get to this part here, we're going to have a fluid that now has low pressure. Low pressure and low temperature, right? So we just dropped the pressure greatly, and with that we also dropped the temperature greatly. And that's perfect, because now this part here, we're inside the space that we want to cool, right? Within that green line. So this will be inside the refrigerator, if we're thinking about a fridge in your home. So this cold fluid is going to go through this guy here, and it's going to go through an evaporator. Now the evaporator, like the name says, the idea is it's going to evaporate this fluid that's going through it. And the idea is, as it's evaporating, what's doing, it's gaining heat, because it's a lower temperature that the chamber or the space we want to cool, it's going to take away heat from that space. It's going to take away energy, right? That's what QL is representing right there. So we have energy going from the space that we want to cool into this fluid that is absorbing energy, and that leaves the evaporator at the same pressure, because no change in pressure took place, but at a higher temperature. So whatever this temperature over here is, I'm not sure what the temperature is, but I know that this is lower than minus 34 Celsius, right? Small temperature. So we just gained temperature going through the evaporator. So after the evaporator, note that now we have a low pressure, low temperature fluid, and the idea is now we want to put this guy, compress it again to be able to repeat the process. So put it through a compressor, and the compressor has to do it. We have to put some work into this guy to work, and then this guy's going to compress, and then we're going to leave this cycle back with a high pressure, high temperature fluid. Now, in this case here, we also have the surroundings over here, surroundings that's kicking in. And if you notice, what the surrounding is doing is giving energy to the system. So what that means is, if I'm taking my my fluid, I'm going from minus 34 on state 1 all the way to 65 on state 2. Okay, I'm increasing the temperature of this fluid, but I have Qin that's giving energy to my system. So that means that my compressor has to work a bit less, right? So whatever the compressor, let's put it like this, whatever the compressor would have to do before, let's put that as just a blank because we don't know that number yet, okay? So if we want to take from minus 34 to 65, it would have to do X work. Just leave X for now, X work. But because we have that Qin going in, it's going to be X minus the 450, is it? Yeah, 450 right there. Yep, minus 450 watts, right? Because the surrounding is actually helping us out in this case. All right, so let me get rid of all this stuff that I just drew, and let's look at what we're have a look about on what the problem is asking from us. So it wants the quality of the refrigerant at the evaporator inlet, the refrigerant load, and the coefficient of performance. So quality at the evaporator inlet. Okay, so it just wants the quality over here. How much liquid, how much vapor do we have on state 4? It also wants to know the refrigeration load, and that's precisely this QL down here. That is how much heat is being absorbed by our fluid every time it goes through the evaporator. And then the coefficient of performance, we all know that. We all know that it's the desired output that we want divided by the required input that we need to be able to get that output, right? So in our case here, the desired output that we want is precisely the QL to be able to keep that guy at minus 30, and the required input is how much energy we need to give to our compressor, Win, right, which is related to this guy here. All right, so how are we going to solve this? We're going to find each of the states. So we're going to find state 1, 2, 3, and 4. The expansion valve, the throttling process, it occurs so that U and PV, these two guys, compensate each other. That is, if this guy increases, this guy will decrease, so that when we go through the throttling process, the enthalpy on state 3 is approximately equal to enthalpy on state 4. Okay, so that makes our lives a bit easier. So what I'm going to do is I'm going to find enthalpy for 1, 2, 3. Then, because I already going to have enthalpy for 4, I can relate that to find the quality. right? The other thing is that if you guys notice, they are asking for the QL, the load in kilowatts. And since we don't have the mass flow rate of the refrigerant, we can't really determine that yet. So we're going to have to find the mass flow rate. And as you can imagine, we're going to use the fact that we know the mass flow rate of water to determine that. Right, so let's get into it. TS diagram to start with. So starting here down on state 1, and I'm going to go through the compressor on a perfect and nice isentropic process over here. Okay, and I'm going to go now through my condenser, and that's going to be a nice isobaric, guys. It's going to go like that until we leave the dome, and then it goes like so, right? Now the throttling process, which is what occurs from 3 to 4, that is, there's no change in enthalpy, but there's a gain in entropy, so it's something like this, right? And then from our state 4 through the evaporator, it's all the same pressure, so it just stays like so. Right, so we would have 1, 2, 3, 4. Mind you guys that as opposed to when we're trying to extract energy, in this case we're giving energy to remove heat, so we're going in reverse cycle. And the dome, if you think about it, number 3 would be either here or as a compressed one, we're not sure yet. We know it's a liquid right after it goes through the condenser. Then 2 hopefully is going to be a superheated one after going through the compressor. And then 1 we're not sure either, so I'm just going to put the dome like that for now, and then we can come back to this if it's not correct. Okay, we have QH over here, and that QH is completely related to, in our case here, completely related to the water that's coming through and grabbing this energy and taking it away. And down here we have QL, which is related to the energy we need to remove to keep the guy at -30. So at this point, it might be easier for you to understand why we have the limitations, right? Because regardless of how this cycle in here operates, and I might just put here that's 134A, so that we don't look at wrong tables. Regardless of how this guy operates, we know that the QH is going to be determined by the 18 Celsius coming in, right? And the QL is going to be determined by the -30 that we want to keep the place at, right? That's the temperature. So that's why we have those two boundary limits limiting the performance of this cycle in here. Okay, so I wrote down what we know, right? We know 1 and 2, sorry, 3 and 4, 1 and 2. So I wrote down what we know. We know 2 and 3 are the same pressure. We know 1 and 4 are the same pressure as well. They've been both given, and I grabbed the temperatures from the drawing. So this is information we have to start with. We also know the mass flow rate of water. So mass flow rate, that's 0.25 kilograms per second. And we know that, like we talked before, the work done by the compressor, whatever the work that has to be done, minus the 450, because that's the bonus we get from the surroundings. Okay, so let's define each of the states so that we can start solving this problem. And as we do that, we're going to find out the quality, which is the first part. Okay, so my state number 1, we have two things for state number 1. We know the 60 kilopascals. We also know the temperature, which is -34 Celsius. Okay, so what I'm going to do is I'm going to do on the first one with you guys, and then the next ones I'll just skip this part, because we're going to do table. This is superheated refrigerant table, so I'm looking at the right table. And I have the temperature table here, and I'm going to be looking at my 34 right there, right? And I'm going to note that the saturated pressure at -34 is 69. Our pressure is smaller, right? So our P, which is 60, right? So our P is smaller than our P sat, and therefore this is superheated. Because this is superheated, we're in the wrong table, so we need to go to the superheated table. It's conveniently down here. And I'm going to be looking at 0.06 megapascals, that's 60 kilopascals. And I'm looking for -34, right? That's my temperature, -34 Celsius. And you're going to notice that we have -20 over here, and we have Tsat, which is right here as -36. So that means that my enthalpy will fall between 227 and 240 kilojoules per kilogram. So I can interpolate that guy there to find my enthalpy, and I did that, and what I grabbed by the end of it was, by interpolation, I grabbed 230.06 kilojoules per kilograms. Okay, I'm going to repeat that process for 2 and 3. So let me go ahead and write down over here H1 is 230.06 kilojoules per kilograms. I'm going to do similar processes for state 2 and 3. So state 2 we know two things about state 2. We know the pressure, which is the high pressure state, 1.2 megapascals, and we also know the temperature 65 Celsius. Okay, so same thing, either by looking at pressure table or temperature table, you'll see, for instance, that T2 is greater than Tsat at 1.2, therefore superheated. Let's just put SH. Superheated, there you go. And then we're going to be looking at table A6, and we can grab enthalpy 2 the same way, and I did 295.18 kilojoules per kilograms. And state 3, it's a similar process, but this time it's going to be a compressed and we know this is 60 kilopascals, 1.2 megapascals, and the temperature just 42. Okay, and then for this guy here, we'll find that this guy is a compressed liquid. So that means I'm going to go to my temperature table. We know that's more precise. And I'm going to do my H3, which will be approximately equal to my Tsat liquid. And that's 111.28. Okay, and that's the interesting part now, because this is, as we noted, similar to H4 because of the throttling. So that means that we know the second information that we need for state 4, right? Because now we just know that state 4 has two things. We know that has a low pressure because it just went through the expansion valve, but we know that it has the enthalpy of 111.28. Okay, and knowing that, we can go now to the pressure table, table A5. We know it's already a saturated mixture, but we can be extra sure by noting that our enthalpy falls between the saturated liquid and saturated vapor. That means we can go ahead and do this, and with this we can grab our quality, and quality ends up being 47.97. And that's the first part, right, because it's asking us what's the quality at the inlet of the evaporator. So we know it's about 50-50, about 50% liquid, 50% is fluid. And we would expect it that after the evaporator we have more, did I say fluid? I meant more gas state, right? So we would expect this gas state to increase as we're going through the evaporator, right? That's precisely the idea. Okay, so that's part A. Now, part B, look here, okay. So part B, we're asked, what is the refrigeration load? Okay, the refrigeration load is QL. And if you guys recall, it's at 1 in QL in kilowatts or watts. So we need a mass flow rate to be able to solve this in kilowatts. How are we going to do that? Well, we're going to use the energy balance principle, right? Because what we have on the condenser is the following. Let's do in green. We have water coming in at 18 Celsius and leaving at 26 Celsius. At the same time, we have 134A coming in at 65, and obviously decreasing because we can create energy, so it decreases to, what is it, 42. Okay, now if we do an energy balance inside this condenser, we know energy cannot be created or destroyed, right? So do an energy balance at the condenser. We know that whatever the energy that is being absorbed by the water has to be being given by the refrigerant, right? So in other words, if I do energy rate, it's going to be the mass flow rate of water times Q that's being absorbed by the water has to be equal to the mass flow rate of 134 times the Q of 134. Right, and now let's break down that equation, because check it out. This Q here is the Q when we go from state 2 to 3. So that's just the difference from state 2 to 3. So we have that. This guy here, we don't have yet, but we can find out, because we know that water going from 18 to 26, we know that we know how to calculate the energy it needs, right, to go from 18 to 26. And the mass flow rate of water we do have. So with that, we can find the mass flow rate of the refrigerant. So let's do that. So the mass flow rate of the refrigerant, 134, has to be equal to the mass flow rate of water, Q of water, divided by Q of 134. Now, the Q of 134 in this case, right, is precisely the QH. So I could rewrite that as QH if I wanted to, just to have less unknowns in this question, right? That's precisely the amount of water energy that's being released. So let's write down what we know about these guys. Oh, and let's write down, before we do that, let's just do what's the Q of water. If you guys recall, it's going to be mass Cp delta T. If I want it in kilojoules per kilogram, I can divide by the mass. I'm going to have Q over 1. This is going to be Cp delta T. Okay, Cp for water at 20 Celsius, you can find table A3. That's 4.18. And then our delta T we have from 26 to 18. So my mass flow rate of 134A is going to be 0.25 kilograms per second times 4.18 times the difference in temperature, which is 8, divided by H2 minus H3. That's 295 minus 111. And this guy turns out to be, well, it's a big number, 0.045454948. Let's just round it up to 455. Okay. And if we wanted to know QH as well, we could also do that by relating the same thing, right? Because the same principle is, as I just said, we could rewrite this equation here as mass flow rate of water, H2, and this has to be equal to the mass flow rate of refrigerants times QH. So if we wanted to know, okay, how much energy is actually being exchanged over there, we could just do the mass flow rate of water times the 4.18, which is the left part of the equation, right, times 8. And that's going to give us 8.36. That's kilojoules per second or kilowatts, right? Don't forget that this guy is kilojoules per kilograms Kelvin. And the difference in Kelvin or Celsius is the same, so that's just going to be kilojoules per second, which is kilowatts. Okay, so what is this number here? This is QH, how much energy is leaving, the rate of Q leaving the system. Okay, and we know also now we know the mass flow rate of refrigerant. Okay, if we want the load, there's two ways we can find the load. Okay, so if you want to know what's the load QL, okay, there's two ways we can find it. I'm going to do both ways with you guys. Okay, if I want to find QL, there's two ways I can go about this. I can do, well, I know QL is the difference when we go from 4 to 1, and I can do that. But I also know that because this is a cycle, right, we can't create or destroy energy. So therefore, as I said, QH is what balances everything, right? QH is what is our limit, right? Because all this energy that's being removed from this environment at minus 30 is then being tossed to QH. So whatever we have going on in the cycle, and we have QH, we have work, and we have the surroundings, and we have QL. So QH has to be equal to the sum of all these guys. QH, QL, work, and the Q surroundings. Right? So you can think about it this way. The amount of energy rejected from the cycle relates to the condenser, right? That's the QH. And it has to be equal to all the energy that the cycle absorbs, right? And the energy that the cycle absorbs is, because the throttling doesn't have any work, then the energy is the QL plus the work of the compressor plus the energy that the surroundings give us. Okay, so either way we can solve QL by doing either of these methods. So let's start by doing just a normal way, probably the straightforward way. Going from 4 to 1 times the mass flow rate of refrigerant. We have all that information. That is about 5.404, and it keeps going 449. So let's just stop there. So the answer that we have. Okay, so it could be as easy as that, but we're going to have to calculate the work of the compressor to calculate the coefficient of performance anyway. So we could have done the other way around. So we could do work of the compressor. We know compressor works when we go from state 1 to 2. So that will be state 1 to 2. And we also have to subtract that 450, right? Now this would be incorrect, right, if we just did this math. Why? Because this guy is in kilojoules per kilograms and this guy is in watts. So that doesn't work out well. So what do we need to do? We need to multiply this guy here by the mass flow rate. And we need to divide this guy here by 1,000, because then we're going to have everything in kilowatts. Yeah, so we have H2, we have H1, we have the mass flow rate of refrigerant. So this guy here is about 2.51 kilowatts. Okay, and then if we wanted to redo with this information, go ahead and do this guy again. We could have. So it's going to be the QL, the 5.404 minus the 2. It'll be the 8.36. If I'm looking for QL, right? It'll be the 8.36 minus the 2.51 minus the 0.45 from the surroundings, which will also give me the 5.4. Okay. All right. So now we need a coefficient of performance. We know that's the desired output over the required input. In this case, our desired output is the QL, the removal of energy from our system, and what we need to input is the work of the compressor, right? And that's why the surroundings help us, because now we need to put less work, 450 watts less. It's not that much of a difference, but it's less work. So this guy is 5.4. And this guy is 2.51. You can do this if you want to, but it's not going to change much. So 251 is my coefficient of performance, and that's dimensionless, right? Okay, so we have A, B, and C. Now, D is the one that asks us for the maximum. Let me reread the question. D is asking us what's the theoretical maximum refrigeration load for the same power inputs of the compressor. Okay, so if we're keeping this compressor at this power here, that is, if we don't want to change this guy here whatsoever, okay, what is the maximum QL that I can have, right? What's the maximum of this guy? What's the maximum energy? What's the maximum energy I can extract from this environment that I want to keep at minus 30? Okay, so we're after the maximum value for any heat engine, for anything operating between two temperatures. These two temperatures are going to limit the efficiency of our machine, right? It doesn't matter how good your cycle is or how bad it is, it will be limited by these guys. And in this case here, we have a refrigerated space at minus 30, and we have a water that's coming in to remove that energy at 18. Okay, so in other words, when we look at this cycle here, right, this QL down here that's being removed from the environment, it's being removed from the environment that is at -30 and that will remain at -30. So that's one of our extremes that limits this cycle in here. The other limitation is this water over here with 18 Celsius. That's another limit there. And note that these two things, they have nothing to do with the cycle. So let's draw this quickly here. Remember when we had the machine with the guy that was claiming to have an efficiency and all that? And because of that, we were trying to figure out whether he was full of it or not. And you guys were seeing what the maximum efficiency could have and all of that. So what he had his limits, and then he was developing this machine, right? And this machine is this thing that I drew here in the middle. And it doesn't matter how good this guy is, all right? It can only have an efficiency, maximum efficiency is related by these outside guys here, right? These guys limit it. And if you guys recall, the efficiency, we had a relationship, I told you guys had a relationship between the source and the sink and all that, but this is for the thermal efficiency. If we're looking at for the coefficient of performance, the coefficient of performance will be 1 over TH or T max if you want T high and T low, or T deep or T cold, like that. One thing that always gets students is this guy has to be in Kelvin, right? Has to be in Kelvin, because if it's not in Kelvin, imagine if you have one of the sources, for instance, is if this guy, for instance, is 0, this guy would go to infinity, right? And we can have 0 Celsius quite easily, but we can't have 0 Kelvin. So in our case here, these two guys limit the cycle, and again, it doesn't matter which cycle this is. It can be the best or the worst, right? It's going to be limited. The maximum coefficient of performance possible out of this guy will be 1 over T high, so that's our 18, the water that's taking away the energy, 18 plus 273 to have it in Kelvin, divided by the 273 minus 30, and that's -1. So that's 5.0625. So we know the maximum coefficient of performance. We calculate, let me do D so this is not confusing. Let's do D. All right, so we know the maximum coefficient of performance is 5. What did we get before? 5.0625, and this is limited by our water coming in and the environment. We want to keep it -30, right? So we have 18 on 18 Celsius. Sorry, 18 Celsius on one extreme, and we have the -30 on the other extreme. And then we know that this is going to limit our maximum coefficient of performance. So if the coefficient of performance is the desired output divided by my required input, then that means that my maximum amount of energy I can remove is the 2.51 kilowatts times the 5.0625 dimensionless, right? So the maximum amount of energy I could remove from this environment, given the water coming at 18 and that I want to keep it at -30, is 12.9 kilowatts. And so that will be the maximum capacity, at least if I want to keep giving it 2.51 kilowatts. Right? That's the best of the best it can do. Right? Hit me up if you have questions. Talk soon.